Hi, my name is Manan. I work as a developer at ThoughtWorks, and as part of working with ThoughtWorks, I get to work with different clients all the time. Over the past 1 year, I had the opportunity to work at Otto, and this talk is going to cover the monitoring setup that we had at Otto, and the tooling and the philosophical practices that we basically used to come up with interesting insights and take decisions. Some of the tooling that I'll mention is probably already going to be familiar with you, but I do hope, because some of these things we built ourselves, so I hope that each one of us can take something from this presentation and apply it on their next system. So before we start, I'd like to talk a bit about Otto. Otto is the second largest e-commerce company in Germany. Amazon basically surpassed Otto in 2014, before which Otto was the first. It began post-World War II when this guy decided to print out pictures of shoes, paste them on a catalog, make 300 copies and deliver to local villages. The orders came in and they hand-delivered these shoes. Over time, they built enough loyalty that now today, Otto is the biggest mail order company in the world. The net worth of the Otto company is $18.4 billion, of which $4 billion comes from their retail. They're headquartered in Hamburg, where I worked with them. This is their premises. The size of the premises in Hamburg is 205,000 square meters. If you're wondering how big that is, that's roughly the size of 35 football fields put together. So yeah, they're pretty big. But when we talk about scale at Otto, we don't talk about the size of their premises. Instead, what we talk about generally is their website, Otto.de. Otto.de on an average gets 1 million visitors every day and registers on an average about 2 orders every second. We could extrapolate from here and say that if an order needs a user to go to the homepage, that by the way is the homepage. If you see, it's rather simplistic. I think that's their key, that they appeal to customers with their simplicity. So the user goes to the homepage, searches for their product, is able to choose their required variant, adds them to cart, registers, proceeds to checkout, finally gets a confirmation. So it's about 8 screens if you look at it, and if you say that 1 in 30 customers convert, it's about 480 page impressions approximately happening every second. We saw that on days when Otto released new offers or schemes or discounts, we saw this number go beyond 1,000 page impressions per second. But this is not a new problem, of course. There are many different domains that face the problem of many visitors. For example, social networking, Twitters and Facebooks basically redefine the scale of customers, the scale of visitors. But what makes this different primarily is that it's e-commerce and we're talking money. So if we're building something and something goes wrong, if there's downtime, there's directly losses that we incur, and nobody likes that. So the first and foremost aim is to keep the website up and running. So we need to ensure that it's running in the most optimal and performant way. We want to build more features, but we want to ensure that we're only building something that leads us to increase our business value and in turn achieve the first point, which is we want to get more money out of the website. So anything that doesn't lead to that objective, we don't want to do. So basically, we want to focus our efforts. We also want to take better decisions, and we found out early on that our features should be able to give us enough knowledge about what to build next. How to go about fixing a bug, for example. What's the best alternative? Should we do a hotfix? Should we wait for the next feature to come around and just then it is automatically fixed? So how should we go about it? So we thought that it's very important that we base our decisions on actual data. Lastly, a point that is often not stressed enough, and I'm going to explain this with an example for here. We set out with the feature, let's say that for our e-commerce company, we want to personalize our users. And let's say we state it in a way that if we personalize 30% of all the visitors coming to the website, then we aim to achieve a total revenue increment of blah, whatever. But we take an assumption that we'll be able to personalize 30% of the customers. Okay, all good. We proceed, we build an MVP, we roll it out, release it. And after we do that, we forget about the basic assumption that we took. We're just concerned with the outcome, the final result. Nobody goes back and matches whether we were able to match our assumption initially. And that's very important, because unless we are matching our 30% number that we initially set out to achieve, we can't possibly say that we are at the most optimum stage yet. So it's important that we base ourselves on important numbers, because we are developers, it's not our job to make up numbers. So yeah, we should base all our decisions on hard facts. So in such a setup, what do we need from a monitoring system? What are all the things that we need? Well, first of all, you need what every other monitoring setup needs. You need the basic database monitoring. You need to know if our SQL queries or our queries to the database are performing slow. We need to know if you need to add an index, for example. We need to know, I don't know, if you need to shard. We need to know all these things. And this is something that most monitoring tools already give you. And we want this information because it's critical. We want standard server metrics as well. We want to know how we're doing in throughput, what are our response times, how we're doing in memory usage, for example. These are important metrics too. Lastly, we definitely want to be alerted if there's something that breaks. If there's an exception, there's an error, we want to keep the downtime to a minimum, and we want to be able to fix them quickly so that we can keep our initial aim of getting more money. But we also want some other things when you base this in an e-commerce setup. The other thing is, we want to measure how our system is doing at any given point in time. And while we say it like that, it's a very vague statement. We can't really measure it. So we decided we need to come up with how do you measure the state of the system. And for this, we turned to the business. And we said, what is this e-commerce system for you? How do you say we can measure it? And they defined it pretty simply for us. They said, okay, for us, orders per second, and the users who are currently on the website define what the state of the current system. And we said this is important metrics too, and these often get missed. And then we noticed that there's two sides of metrics about a system. There's performance metrics, if the website is running efficiently and optimally, but there's also business metrics, which also tell you if your website is performing optimally or not. So we thought this was pretty important. The monitoring setup should be able to allow us to narrow down on the sources of potential bottlenecks before they actually happen. So while we are great with alerts and getting, okay, there's something broken, we'd like to know before it actually breaks. So our monitoring setup, if it equips us with this, will be great. And lastly, we want to validate our business assumptions, just reiterating our initial points. We want to know if we achieved the numbers that we set out to achieve. Right, okay, moving on. So most monitoring systems today are based upon logging. We base most of our alerts, most of our systems on logging, and we rely on them on getting insights, which is great. Logs are the developer's best friend. They pinpoint at the actual source of error. They tell you the exact line number in the code. They tell you the character number, in fact, and that's all great. They help you extremely well in telling you exactly where the problem is after there's a problem. And that's the basic and inherent problem with logging. Logging is implicitly it's reactive, and this, for example, is a scene from Dragon Ball Z. I'm not sure if any of you watched it. It's here you can see the protagonist Goku fighting with the villain Frieza, and what happens ultimately is that the planet is about to explode. And I like to take this. I kind of feel this way once I get a logging-based alert that the planet is about to explode, and I need to fix something. And nobody likes to work under such high pressure. So I mean, logs are great. If it weren't for logs, we would be sitting on that planet drinking beer and not knowing if there's something wrong. But can we do better than this? The second problem with logs is the sheer signal-to-noise ratio. With distributed systems, microservices, or distributed teams, each and every small component of your system needs to be wired up with logging. And then there's just so many logs for finding that one error that may happen soon in one of the files in one of the systems. I mean, there's wonderful tools out there now, the Splunks, the Elk Stack, and everything, which allow you to do analysis and find out what exactly the problem is. But there's still, you need to know what systems you're integrating with, and as a new person joining a project, it becomes increasingly difficult. So signal to noise ratio is pretty terrible with logs. We realized that while logging is about scattered incidents in the system, about occurrences, about accidents that happen in the system, we noticed that metrics helped us in actually understanding the state of the system and gaining valuable insights. And they helped us in doing this at any given point in time. So we realized that metrics are perhaps a better basis for a monitoring system in an e-commerce setting. So we set out to build this monitoring system based on metrics, and we said that we can do it in 4 phases. The first phase comes as capture or collect. And we wanted to collect as much data as we can. At the same time, we wanted to be reasonable, because while you can go ahead and collect all the data in the universe, it just increases your clutter. So we said that it was very important that we collect only the data through which we can get meaningful insights. So I think this statement from Datadog website basically says it correctly because they put the word reasonably in there. Be reasonable in what data we collect. And we use the metrics library. For those of you who maybe they're not aware, then this is a library written by Kodhe, and he presented this at the Pivotal Labs meetup. There's a wonderful, wonderful talk. It's called Metrics Everywhere. And I urge you, if you haven't yet seen it, I urge you to see it. The references would be included in this presentation as well. Metrics basically allow you to measure what's going on in the system, to instrument themselves in code, and know the behavior of your code while it is running it in production. And we found out that including metrics was really simple. The project was in Clojure, so most of the examples here would be Clojure, but they have a port for most popular languages like Java, Scala, and others as well. So we noticed that it was as easy as including a dependency, creating a registry. A registry is basically just a container for all your metrics, so that you're able to divide between all your systems, so that you keep all the metrics of one system or one whatever domain in one container. Choosing the right tool out of the metrics tool set. In this example, we're using a counter. We'll go ahead and explain counters and other things in brief very soon. And then basically instrumenting them in code. Taking care of when we have to instrument them is under your control, because you know your code better than any other software does. So what are counters? Counters are excellent metrics in cases when you control when something is opened or closed, or when you control when something is added or removed. A great example for this is HTTP requests, for example. So if you're using a rack-based stack or a node-based stack, then you can just put in that middleware that basically as soon as there's an incoming request, you increment this counter, and as you've served a response, you decrement that counter. And they give you a useful insight at any given point in time. They tell you how many open HTTP requests are going on in the system at the moment. Another useful metric is gauges. Gauges allow you to measure instantaneous value of something in the system at an instant. So these are generally used for things that you configure and are not directly influenced by users' behavior. For example, something like if you're using Redis, then Redis used memory. And this can give you interesting insights about your system. If, say, the Redis memory drops suddenly, then are we expiring too many keys together? Do we need to rethink that? How is our disk usage doing? Is our Redis memory almost full? And they were good metrics for that. Sorry, connection loss. Another good one was meters. Meters allow you to measure the rate of something. And they're especially good for things like throughput, to measure how many requests we're serving at any given point in time. While these were great metrics to measure performance, we saw that our system is better represented in terms of these other metrics. Counters can be used to measure the number of users we are personalizing at any given instant. So they could be as easy as if you're serving any personal recommendations to a particular user, then increment this counter. And they give you interesting insights about whether we are personalizing any users or not. Have our pattern of how many users we personalized changed in the past. And they help us in solving the initial aim that we set out to achieve, which is personalizing users. Gauges, for example. So in our system, we were doing a lookup of from all our products on the website. And for that, we were caching all the products. And let's say there's 20,000 products, then a gauge can give you an instant value of how many products are cached. And say this value decreases to 20, and you start noticing things like, okay, we're not recommending anything anymore. And then you can directly correlate, we're not recommending anything because the number of cached products is just too less. And say we're recommending too many recommendations, then perhaps the number of cached products is too many, and you could correlate. Something like meters were especially good for methods where checkout happens, for example. And you can see instrumenting them is pretty simple as well. The next one is histograms. Histograms are great for measuring for measuring data that corresponds to responses. For example, what do you respond with generally? Let's say you have a search in your application, then how many search results do you return generally? How many search results on an average? How many search results do 99% of your users get? And we thought that this was a great metric as well, especially for measuring something like this. How many of our customers are getting 5 personal recommendations or less? And we thought this was a great number because this is what matters at the end of the system. If this number is too high, then we are perhaps giving too many recommendations and matching too much. And if this number is too low, then perhaps we're not optimal enough. Timers are a bit complex, and they allow you primarily to measure the time it took to respond. But they also have a meter built in, and they allow you to correlate the time it takes you to respond to something with the rate. So for example, a very useful metric when it comes to timers is, it took us 80 milliseconds to give recommendations to 99% of all our customers when the number of requests, the rate of requests, was 300 requests per second. And then, on the flip side, let's say it took us 200 milliseconds, the same number that was 80 milliseconds suddenly took 200 milliseconds when the number of requests changed to 800 requests per second. So this was useful insights. And so again, instrumenting them is pretty straightforward. Just since you know where these actions are taking place in your code, you exactly know where to put these metrics. So we're done with the first part, and we said we've captured all the important data that we needed to collect. The next part was aggregation, making sense of whatever we've collected. See if we can actually make any use of the information that we've collected. And for that, we used Graphite. Graphite, for those, in case you don't know, it's a time series database, and it allows you some graphing capabilities. It's pretty old, and I think there's a lot of new solutions out there with the InfluxDBs and the Prometheuses. But I think for our use case, Graphite did the job. We chose it because of the graphing ability that it gives you. It allows you to see graphs out of the box as images. It even gives you a JSON endpoint, which you could use to basically do things like alerting, for example. It also provides you a query DSL and allows you to apply mathematical functions on the data that you've collected. So transformations become increasingly easy. Graphite allows you to run itself in a distributed node. So for our project, since we were such a big website and so many customers, so many teams, there was a lot of metrics being collected. On an average, each system collects about 40-45 metrics and scales really a lot with the number of systems. So we thought that this was really nice. So as soon as your application send data to Graphite, they go to the Carbon backend and are kept in the Carbon cache. And the Carbon cache regularly flushes these events to disk as and when it can. And when you want to pull out a graph based on these events, then the Graphite web looks not only in the disk, but as well as in the cache. So your data is almost always up to date as well, which was another reason why we chose the Graphite. The next step after aggregation was visualization. We wanted to see if we can get, in a glance, we can know what exactly is going on with the feature. And for that, we tried using Graphite Web, and we saw that this would just not suit our needs. First of all, it has graphs that look like that. And we found out that that there's other shortcomings. There's other shortcomings with Graphite Web as well. In case we want to drill down and know exact values of something at any given point in time, it wasn't really helpful, and it didn't really help us there. The graphs are pretty much non-interactive. They're PNGs, and you can't really do anything with them except for looking at them. The query language and the editor that Graphite provides is quite prone to errors, and it's plain text. So it's very easy to make a spelling mistake or missing a bracket, for example. And it was very difficult to correlate any change in the graphs with events in the system. For example, if something changed, we want to also know what happened at that very instant. Was there, say, a deployment? Was there, I don't know, a new provisioning? And Graphite didn't tell us this. So we went ahead and we wrote something ourselves. This is called the oscillator, and it allows you to create nice dashboards. It takes Graphite as a source at the back and hits the Graphite as JSON endpoints. It's written in Clojure and uses D3 for the front end. So the charts that you make are essentially very interactive and give you instantaneous values. You can drill down. Actually, I have maybe I can just. Yeah, there's a demo that I'll just show you in a second. Including oscillator in your project is as easy as defining what your page should look like. Saying, okay, I need a chart of this type. The types could be a line chart, which is the default. It could be a bar chart. It could be a pie chart, in case anybody has interest in those. And you tell what your chart is called. And later on, you can define your chart in simple Clojure. You define what the Graphite target is. If you notice, we also open sourced a Graphite DSL, which allows you to do this Graphite applying mathematical functions on the Graphite targets, and takes away some of your, well, you probably won't make that many errors as you would have if you were writing plain text. And you can define the colors. You can also define the type of chart it is, whether it's stacked or not. For example, the previous example that we saw, this is a stacked graph. And you could have a line graph as well. So, let's see. Right. Okay, this is. Okay, please tell me if it's not really clear. This is probably not. Okay, so this is, for example, a dashboard. The size is a bit off because of the display settings, but essentially you prepare your own dashboard. You can have images or graphs, and the graphs basically look something like this. So if you see, it's very interactive. If you hover over it, it tells you exactly how many user requests we were serving at this point. It's basically graphing a counter. You could easily drill down and increase the time. So you can say, I want to look at events from the past 2 hours, not just 1 hour, or the past 24 hours, for example. And it can do that for you. It also manages to distribute all the data for all your environments. So you can see data separately from your development environment or from your production, from staging or whatever you may have, and you define it yourself. You can also aggregate data on a minute basis, on a 10-minute basis, or on a 30-minute basis, and see the graphs change. So we thought this was simple and good enough, and was pretty useful for us. One very interesting feature of the oscillator is annotations. So events that may directly and majorly influence your system, events like deployment or adding or scaling up, scaling down, these events should directly be available in plain sight on all the graphs so that you can directly correlate changes in the graphs to these events. So maybe I have another example. So this, oops. There you go. So this graph, for example, if you go back, so I think it's not visible here because of the display, but essentially it shows you small annotations along the timeline and shows you exactly that there was a deployment happening at this moment. And then if you notice changes in the graphs, for example, if the graph suddenly drops or suddenly increases, you can directly correlate it to changes in the deployment, and you can proceed from there. So we had certain learnings from all this this basic graphing and metrics, and some of those were, first of all, it was very important to choose the right metrics. We noticed that often when somebody asks, okay, I need to know more about the system and I need to have information, I need to have metrics, the first thing that comes to people's mind is plotting the CPU load, for example. And I found myself quite curious because I personally didn't know exactly how CPU load is calculated, so I started Googling, and there were plenty of posts around this, and people saying whether it even makes sense as a metric or not. And then I basically kept Googling and found out, okay, what causes CPU load to spike? And I found out the Stack Overflow post, and I trust this guy because he has a lot of votes and everything. And he basically says that you could hit one core's worth of CPU by just parsing text. And this is perhaps not a very useful metric to plot on a graph because I don't want to know if there was high CPU usage if all I'm doing is parsing text. I'm going to be parsing text. That's what my application does, and I need it. So what we found out was that we should always try to use simpler metrics, something like how many users currently on the website, what is the disk utilization. We saw that simple metrics make more sense than complex metrics like CPU load. Another learning we had was that mean values or average values are pretty absurd at quite a few times. For example, we had a Redis server, and we basically wanted to keep an eye on the response times we had from this Redis server. And we noticed that on average we were always under 20 milliseconds in responses. And we said that's good enough. With the team that we are integrating, we have a contract that we'll always serve within 80 milliseconds, and 20 milliseconds is like, wow, that's pretty fast. And then we noticed that the other team was running into circuit breakers, timeouts. And then that's when we realized that we were basically doing it wrong. Plotting average values of response time make no sense. It's much more important to plot max timings, or what is the time of the 99th percentile, for example. So that's the average values, and that over there is the max values, for example. So you can notice that they could very easily have a difference, and this is quite often above 100 milliseconds, for example. And this was useful. So in things like response times, it's nicer to see how long we're taking for 99th percentile or the maximum over time. So yeah, mean can be pretty absurd, so choose wisely. We also saw that we must choose the right metric for the job. So histograms, for example, are perfect for things like how many personal recommendations are we serving to a user, and for example, how many search results are we getting. Counters, again, perfect for how many connections, and so on. So finally, we've managed to capture, aggregate, and visualize the data, but nobody's going to keep looking at it, and we want to go and sleep at night. So we saw that we needed alerting, and being the team that we were, we always wanted to keep things as simple and plain, and we decided to write a simple alerting library in Clojure, and you could just define your alerts like this. So you say something like start check and your condition, and in this, since it's just code, you could essentially do anything. You could connect to your database, you could connect to the graphite and see if the metric is right, if the value of the metric changes too frequently. I mean, and and basically basic health checks are possible as well. So this keeps things simple, and then you just define what happens if there's an error and what happens if there's a success, and you define what to do when there's an error, and you basically just do it in Clojure. You just say what happens when I want to alert someone, and the alerting function could be right there. In this example, we can take the console. You could just as easily send an email notification or a Slack notification or anything you may have. And it also gives you a nice dashboard, as if dashboards were not already enough. It gives you another one, and it gives you like a nice view for your entire ecosystem, all the checks, and you could even drill down into each one and see why it is red and what happened when it was green. So we thought that this was really good. We found these alerts to be of extremely high importance because every morning we used to come in and the first thing we used to do was take a look at these and then decide the priorities for the rest of the day, because this was mostly live checks and they were a single source of truth, and we found ourselves relying more and more on these checks. So we included them in our definition of done. So every story or every feature that we were building, we said that once that is complete, we would not be moving the story on until and unless we add the relevant checks or modify the existing checks accordingly. And we saw that it was very important to make it as visible as possible. So we had emails, Slack notifications, as well as the dashboard in plain sight. So that was mostly all the monitoring solution, and it can be defined simply as capture, aggregate, visualize, and finally alert. And that pretty much defined most of the monitoring setup we had, and we found this to work for us. So there was one missing piece still in the puzzle, and that was, so we found out exactly when something went wrong. We found out, okay, this metric suddenly dropped, okay, this suddenly changed in a way that it wasn't supposed to change. We were able to find this out from our graphs or from our alerts. At the same time, the time to fix these things wasn't changing. And we found that with continuously deploying small changes, then monitoring what happens with those changes, and seeing if there's something wrong, then we could easily roll them back and redeploy one thing at a time and arrive at exactly what is breaking. So, for example, our biggest deployment was, I think, 15 commits big at some point in time, and that's, I guess, pretty small. So once we saw that there was something broken after we deployed those 15 commits, we just rolled back those 15 commits, loaded them one commit at a time until we found out exactly which commit was breaking something, and we could just find the problem like that. So it's a matter of practice as well, that this ended up being the missing piece in the puzzle, and we could just complete our entire monitoring setup by following this ideology. I'd like to finish by this a small note on software that pretends to basically do everything for you. You just plug it into your application and it ends up monitoring everything. It just sounds like they know your system better than you do, and that's never the case. So I think it's very important that we realize that nobody can know the system better than the people who write it. So I think for us, instrumenting checks in code made more sense than just plugging in something. Because the only way I can understand that such tools could work is they could maybe hook into individual function calls and each and every function call, and that could hardly be efficient. They're usually proprietary, very expensive, and I can see no reason to use something like this when a great monitoring setup is possible for free with open source softwares. So we really couldn't find any use for those proprietary tools. That's about it. These are the references to all the things that I mentioned during the talk. That's the metrics talk that I talked about, the projects for Oscillator, and X-Ray is the alerting library that I spoke about. And finally, please go read the AutoDev blog. They share interesting an idea.